Hello again, problem solvers. We have got two more lessons before Easter break here. This one is on sums and products. We did functions, we did algebra. And you think algebra would be sums and products, but we're going to be more general here. We're going to talk about not infinite sums, but just big sums and big products. So the sigma notation you see there, that's for adding up a bunch of individual terms. So the subscript I there indicates the different things that we're adding up, but sometimes we put n on the bottom. It really depends on just the book or the application. If we want to multiply a bunch of things, we use a capital pi. That thing looks like two pillars. That is the capital letter pi. And the other one is a capital sigma. There are also some specific series that we want to talk about. You learned about geometric series in Calculus 2, but here we also have an arithmetic series where rather than multiplying by the same number, you add the same number. So here D is the thing that you're adding. You start with this initial value A, and then you add D, and then you add D again, and you add D again, and so on. Geometric series is where you have a ratio that you multiply by. So you start with A, you multiply by R, you multiply by R again, and so on. Geometric series and arithmetic series both have a nice formula for adding them up. And so what they call here the Gaussian pairing tool. This is the idea that we did a while back with symmetry, where we added forwards and backwards. So think of this sum. A is the first term, L is the last term. So this is a finite sum. And then the second line is I added it backwards. I rearranged everything, and then I summed those two lines. And every pair of terms becomes a plus L, and you have n of those, right, because you had n terms, but on the left you have 2s. So divide by 2 and you get that. So you take the first term, you take the last term, you take their average, and you multiply that by the number of terms. Geometric series, we're going to use a telescoping tool. So I never proved this in Calc 2, but this is where that finite geometric series sum formula comes from. So we have S, and then we multiply everything by R to get a new expression there in the second line. And now we're going to subtract these lines rather than add. And if you look at them diagonally, they cancel. You have the same thing a bunch of times, except for the A on the top doesn't cancel, and then the last term on the bottom doesn't cancel. So you get A minus AR to the n, and then that's S minus RS. You factor the capital S out, you divide, you get that expression on the bottom, and that is the expression you guys learned in Calculus 2. If you go infinite, then the R to the n, assuming R is less than 1 in absolute value, that goes away, and then you get the A over 1 minus R formula that you guys already know for infinite geometric series. Telescoping series are things that can collapse easily. So here's an example. I want to find the sum of 1 times 1 factorial plus 2 times 2 factorial, 3 times 3 factorial, all the way up to n times n factorial. Each term I have in this sequence is k plus 1 times k factorial minus k factorial. That's a goofy way to write it, but I'm kind of thinking outside the box here about what was originally k times k factorial. So add one more k factorial and take it away. And the reason why I can do that, if you look at the top right of the first line, now that's just the difference of 2 factorials. And then now if you write the sum out, you have 2 factorial minus 1 factorial, add 3 factorial, subtract 2 factorial, and the next term you'll add 4 factorial, but then subtract 3 factorial. So everything cancels except for that minus 1 at the beginning, and then the very last n plus 1 factorial. So we call it a telescoping series because if you've seen Pirates of the Caribbean or another pirate movie, their telescopes would collapse, and like this thing collapses.